In this presentation, we shall learn according to new WBSCTE syllabus of Applied Physics for Semester 1, Unit 6 about heat and thermometry. Here we shall cover Unit 6.1 going through concept of heat and temperature, basic concept of measurements of heat and temperature, modes of heat transfer, conduction, convection and radiation with examples, coefficient of thermal conductivity, simple numerical problems. Here the students will be able to, number 1, state the concept of heat and temperature and differentiate them. Number 2, describe basic concepts of measurements of heat and temperature. Number 3, state and differentiate conduction, convection and radiation. Number 4, cite examples of conduction, convection and radiation. Number 5, define thermal conductivity with its unit. Number 6, solve simple numerical problems. Heat is the form of energy that gives us the sensation of hot or cold. For example, the tea is hot and the rainwater is cold. From kinetic theory of matter, we know that the molecules of all substances at temperatures above 0 Kelvin vibrates with more kinetic energy when the substance receives some external energy. So heat energy is the sum of kinetic energy of the molecules that is transferred from one body to another due to the difference of their thermal state. Different forms of heat. Number 1, sensible heat. This causes change in the thermal condition of a substance. Latent heat. This causes change of state of the substance at some thermal condition. Radiant heat. This travels from the source as electromagnetic radiation. Temperature measures the degree of hotness or coldness of a body. The thermal state of a body determines how much heat will be given out. If two thermally connected bodies are in same thermal condition, they are said to be in thermal equilibrium. Zeroth Law of Thermodynamics. If two bodies A and B are in thermal equilibrium with a third body C, then the bodies A and B are also in thermal equilibrium. We see this in the figure in the top right corner. Temperature of a body is the measure of its thermal state or condition. Temperature of a body is a measure of the average kinetic energy of all its constituent particles. RMS speed of molecules is proportional to the square root of the absolute temperature of the substance. Differentiate heat and temperature. Number 1, heat. It is a form of energy that travels between bodies. Temperature represents a thermal condition of a body. Number 2, heat may be regarded as the cause. Temperature may be regarded as the effect of heat. Number 3, equal heat content in different bodies may not lead to their equal temperature. Equal temperature of different bodies may not lead to their equal heat content. Number 4, during change of state of matter, the heat content changes. During the change of state of matter, the temperature does not change. Measurement of heat. Heat can be measured by the extent of effects it produces on the body it heats up. The easiest way of measuring heat is to note the rise in temperature of definite mass of the body. In CGS system, the unit of heat is calorie. In SI, the unit of heat is joule. 1 calorie is the amount of heat energy required to raise the temperature of 1 gram of water by 1 degree Celsius. The picture shows rise in temperature by 1 degree Celsius when 1 gram of water is heated by 1 calorie heat. Measurement of heat. If the heat needed by a body of mass m gram, specific heat capacity C calorie per gram per degree Celsius is H calorie. When it is heated through theta degree Celsius, then H is equal to mc theta. To express H in joules, multiply value of H in calorie by J equal to 4.2 joule per calorie. Here J is known as the mechanical equivalent of heat. Here we have a problem. The question is, what is the heat required in joules to raise the temperature of a substance of mass 50 grams and of specific heat capacity 0.8 calorie per gram per degree Celsius by 30 degree Celsius? The answer is given. The mass m is equal to 50 grams. The specific heat capacity C is equal to 0.8 calorie per gram per degree Celsius. The rise in temperature theta is equal to 30 degrees. Here we use the formula, that is H is equal to m into C into theta. Putting the values, we have 50 into 0.8 into 30 calories, that is equal to 1200 calories. Now since we know that 1 calorie is equal to 4.2 joule, we multiply 1200 by 4.2 to obtain the result in joules, and we get it is equal to 5040 joules. This is the answer. Calorimetry is the study of measurement of the quantity of heat. Principle of calorimetry. The heat released by the hot body is equal to the heat absorbed by the cold body. Calorimeter. The device used for the measurement of the quantity of heat transfer is called a calorimeter. The picture on the right shows a simple calorimeter. The main limitations of calorimetry are: number 1, losing heat to the environment, and number 2, uneven heating. Water equivalent. The water equivalent of a substance is equal to the amount of water needed to absorb the same amount of heat as the substance does for 1 degree increase in temperature. Therefore, water equivalent of a body equals the product of its mass and its specific heat. Temperature of a body is measured by a thermometer using the property of thermal expansion of the thermometric liquid. So what is a thermometer? Thermometer is an instrument for measuring temperature. Two types of thermometer are there. Number 1, glass thermometer using mercury or alcohol as the thermometric liquid, and digital thermometer that uses electronic heat sensors for the measurement of heat. Glass thermometers are of two types. One is clinical thermometer, where the temperature is generally measured in degree Fahrenheit. And number 2 is the laboratory thermometer, where the temperature is generally measured in degree Celsius. Scales of temperature. Every temperature scale has mainly two fixed points. One is known as the upper fixed point, taken at the boiling point of water, and number 2 is the lower fixed point, that is taken at the melting point of ice. The difference of these two fixed points is called the fundamental interval. According to convenience, the interval between upper and lower fixed points is divided by 100 in case of centigrade scale or Celsius scale, and by 180 in case of Fahrenheit scale. Each such division is a degree in respective scale. For each scale we can write thermometric reading minus lower fixed point by fundamental interval, which is a constant. The choice of mercury as the thermometric liquid has following advantages. Number 1. Mercury has a wide range between its melting point, that is minus 39 degrees Celsius, and the boiling point, that is 356 degrees Celsius. Number 2. The thermal expansion of mercury is sufficiently uniform in this temperature range. Number 3. The specific heat capacity of mercury is quite low at about 126 joule per kg per Kelvin. Number 4. Mercury has high thermal conductivity as it is a metal. Number 5. Mercury is an opaque liquid. This helps seeing the edges and tip of the thread properly. The choice of alcohol over mercury as thermometric liquid has following advantage. Alcohol has a wide range between its melting point, that is minus 200 degrees Celsius, and the boiling point, about 78 degrees Celsius. Scales of temperature. Here we can see three different temperature scales. Number 1 is the Celsius or the centigrade scale. Number 2 is the Fahrenheit scale, and number 3 is the Kelvin scale. Here the values of the upper fixed point in the three scales are shown at which the water boils. Next we can see just above the thermometer bulb the lower fixed point in these three scales at which the ice melts. Even below we have noted the values of the absolute zero in the three scales at which the molecular motion is thought to be ceased. The relation between the three scales with the temperature to be measured is shown below according to the ratio as we have learned in the previous slide. Now we read about transmission of heat. Heat is the energy in transit. There are three different ways in which heat is transferred. Number 1. Conduction. It takes place mainly in solids where the thermal vibration of the constituent molecules is transferred to the next. The picture beside shows conduction of heat along the arrow with decreasing temperature with distance. Next is convection. It takes place in fluids, that is liquids and gas, where the energized molecules at heated regions move to the colder region and transfer their energy to the other molecules. Radiation. Heat is transferred from the source as electromagnetic waves without requiring a material medium for its propagation. The picture beside shows As seawater is heated due to solar radiation, convection current in moist air takes place that rises up and condenses to form clouds. Coefficient of thermal conductivity. The heat energy Q flowing in time t through a cuboid of area of cross-section A and length x when the temperature of the faces 1 and 2 are theta 1 degree Celsius and theta 2 degree Celsius respectively can be written as Q equal to K into A into theta 1 minus theta 2 into T by x, where K is called the coefficient of thermal conductivity, that is given by K is equal to Q by T into x by A into theta 1 minus theta 2. Coefficient of thermal conductivity is the rate of heat energy flowing through a unit cube when the unit temperature difference is maintained between its opposite faces. The SI unit of the coefficient of thermal conductivity is watt per meter Kelvin. Composite slab. Two slabs in series. Heat Q flowing in time t through two slabs of conductivities K1 and K2 and length x1 and x2 having same area of cross section A in series contact with each other maintains temperature theta 1 and theta 2 degrees Celsius respectively, where theta 1 greater than theta 2 at phases 1 and 2 at equilibrium. The temperature of the junction is theta degree Celsius, given by theta equal to K1 x2 theta 1 plus K2 x1 theta 2 by K1 x2 plus K2 x1. And x1 plus x2 by k is equal to x1 by k1 plus x2 by k2. In special case, if x1 equal to x2, then k is equal to 2k1 k2 by k1 plus k2. Two slabs in parallel. Heat Q flowing in time t through two slabs of conductivities k1 and k2 having area of cross section a1 and a2 and length x in parallel contact with each other maintains temperatures theta 1 and theta 2 degrees Celsius respectively at the faces 1 and 2 at equilibrium. Here k is equal to k1 a1 plus k2 a2 by a1 plus a2. In special case, if a1 equal to a2, then k is equal to k1 plus k2 by 2. Thank you.